there also can be seen this this upper level low here. It's associated with high IPV values, and you can see this clearly with this purple color in the satellite image. Let's have a look at the general situation in 500 hectopascal geopotential and temperature. Also at 500 hectopascal, you see this cutoff low here is moving northeastward over France, so that we got a southerly or southwesterly flow over Central Europe, and there was a very hot and violent air mass evacuated from northern Africa in this region. You can see this here at the 850 hectopascal temperature and the mean sea level pressure. The mean sea level pressures are the white lines, and the geopotential at 850 hectopascal are the black lines, and the shading colors are the temperature, and it's also very hot air mass. 850 hectopascal temperature reaches nearly 20 degrees. Ahead of this cutoff low, there was a low at the surface developing here, and you see here this is the cold front, warm front, and you can imagine this is a really severe situation. And when this trough was moving to the east, you see that there is a little bit then at the Alps, and there will be a Lee cyclogenesis here at the northern flank of the Alps. And it was a really violent air mass. You can see this here in the Cape values, and they are really, really high. I not often seen such high Cape values over Germany, and this was the model prediction here, up to 3,000, 4,000 joule per kilogram here at France, at the border to France, also over northern Italy. The wind barbs you can see here is the shear vector from 0 to 6 kilometers. And there's sufficient shear for supercells over Germany, and very high shear values over northern Italy. And it's a really explosive situation there, and might be could be an outbreak of severe storms. And lots of the shear over Germany, most of the shear was in the level between 0 and 3 kilometers. And let's remember this later. This will become important as we see then later. How was the situation at the noon? You can see here a satellite picture. There was a EUMeNWP picture in true color available at this time. You see here this Saharan dust, which is induced into the warm conveyor belt of this low pressure system, and it complicates the forecast a little bit, because it's often so that there will be zeros caused by this Saharan dust, and it will lower the insulation, and then you get problems with convective initiation, and many of the models do not take this Saharan dust into account. You can also see very clearly in the dust RGB, and this purple colors here, there's a lot of dust. Some storms are already ongoing, but there are a lot of cirrus clouds, dust-loaded cirrus clouds, and medium high clouds in this area. So let's have a look at the storms. We see here the sandwich RGB, and there are quite a lot of storms here. Some stronger ones over northwestern Italy and Switzerland. And I have to say, this is a blended image. You have this true color image, which is blended with the 10.8 infrared channel, which is semi-transparently over the highest clouds. So you get this image. We often use this at DWP for nowcasting, and you can here have a closer look at this. Regarding to MTG, I used the Xiaomi picture because I hope in the future we will see this similar like this in a very high resolution. There you can see a lot of upper level features here. At the storm overshooting top here at this point. The temperature, cloud top temperature, reaches almost minus 70 degrees, and you see such a kind of cold ring. So it indicates that this overshooting top penetrates tropopause. This seems to be a very severe storm. This is the old cluster here. It doesn't go so deep into the tropopause. It is not so healthy anymore. You can also see this a little bit at MSG, severe convection RGB. Therefore, you can distinguish here between small ice crystals in the clouds, which are from strong updrafts, and bigger ice in the clouds, which are here in the anvil, and water droplets. And you can see a little bit in the updraft, but it isn't so not easy to see. So I tried something to do such severe convection RGB with the EUMeNWP picture, and these are the colors from the general severe convection RGB. For the red channel, generally it's used the water difference of the water vapor channels, and the green are infrared different from the infrared channels, so that you can distinguish between the small ice crystals with getting this yellow color and this bigger ice crystals, and the blue channel is near infrared and visible to see the water clouds. And because in the EUMe picture, these water vapor channels are not available, I replaced this by this infrared channel, and I hope this will not matter too much. And I think you can see this here better, that there's a very strong updraft in this cell. This is very, very healthy, and when you have a look at half an hour later, you see that the storm is really exploding here. And this is an older storm here, and these storms over France aren't so intense, but here there might be some convective initiation in this area. But let's focus on this storm. There was a sounding available for Novara Cameri. It's in Piedmont and it's northwestern Italy, near the storms. And what do you see here is very fat cape. You have cape values, ML cape around 2,600 joule per kilogram. It's really a lot. And there's also sufficient shear here, 60 meters per second, to produce supercells. And there's a very deep warm rain layer which leads to high precipitation. What do I mean with this? You see this layer here from the LCL. This is the path of the air parcel, and here it reaches the 0 degree line, and this area here is very deep, and this means there's a lot of warm rain. Will be a lot of warm rain in the storms, and this is very effective in the precipitation, because in the warm rain you have these evaporation, and there will be a threat of flooding there. So you saw the storm, you saw the sounding, and now I ask you if you can make a hail size estimation of that storm in northwestern Italy, and how do you think, how big are they? 7 centimeters, 6 centimeters. Someone more than 7 centimeters, 8 centimeters, all around 7 up to 8 centimeters. Okay, up with 8 centimeters. Okay, really big hail, 8 centimeters. We will see what happens. But let's go forward. Here, this is the radar picture, which see what happened here in Switzerland and in Italy. It starts at 14 UTC. The storm was decaying, but there were a lot of other storms developing in this region, and all developed at this path here. And this, where some of them were supercells with very heavy precipitation, and what you can see, this is a back-building storm. That means they will initiate new convection at the southern flank at this, and this will lead to a lot of precipitation here in this area, and there were severe flooding, some mudslides. Here's the measurement of the precipitation, the accumulated precipitation during that day, and there were around 160 millimeters, but in a few hours there are unofficial measurements up to 200 millimeters, and it was very severe weather. And when you had a look at the situation, you expected more isolated supercells, but the storm training, I think, wasn't so expected, and unfortunately there were a few fatalities in Switzerland. These are the ESVT reports, and this was our storm, our supercell we talked about, and there were really 10 centimeters hail size here. It's really giant hail. This was a typical sounding for giant hail, because you had a lot of cape there, a lot of cape above the minus 10 degree, and sufficient shear, good inflow, and all ingredients were met. So let's have a look at the other regions, especially for southwestern Germany. There was a sounding available at 12 UTC at Stuttgart, southwest of Germany, and you can see also here bad cape values. There was a stronger cap. You see something around 100 joule per kilogram, so convective initiation wouldn't be so easy in this air mass. Here's a little bit of inversion, but of this there's an elevated mixing layer which provides this bad cape values. I never seen such high cape values in Germany even before. A new cape around 5,000 joule per kilograms. This is really amazing. And when there will storms happen, they will develop easily into supercells with very large, even giant hail. And but as I said, it's not so easy to initiate the storms. But when you remember, there was a cold front approaching from the west, so you need a widespread lifting mechanism, and this was given with this cold front. So there will be a squall line or a bow echo, perhaps, and it's this shear here, it's 18 meters per second. It's enough for supercells, and most of the shear was between 0 and 3 kilometers, so 15 meters per second. You see this in the autograph. The red color are the lowest 3 kilometers, and this was the storm motion. This is your bunker's right mover, where supercell, and the front is orientated in north-south direction here, and moving slowly to the east, and the shear vector is perpendicular to the front, so it will be perpendicular to the line, and you have also here some dry air, and this is good for a squall line or bow echo. See this here and this. When such a storm develops, you usually have some precipitation, and this precipitation can evaporate here in this very dry layer here. It's from the elevated mixing layer, and you get a lot of evaporating cooling, and so you have a cold pool in the wake of the storm. And normally without shear, this cold pool will spread out and cutting the updraft, and the storm will die. And what makes the shear, when you have the shear vector perpendicular to the front or to the line, you get here such a vortex. It's it's a vortex line, horizontal vortex line, and this vortex causes that this cold pool stay nearby the thunderstorms, by the storms. They hold back this outflow from here and hold it near by the storm, so that you can have a continuously updraft in this region. And here you have also a mesoscale updraft. Here underneath in this cold air, you get a high pressure system. Yes, you have an updraft. Yes, and here in this part you get a divergence. There is here a negative pressure perturbance, so you can get a real inflow jet here. That the air will inflow from the rear at mid levels. It's very dry air usually, and you get here a lot of evaporating, and the cold pool strengthens, and this pushes the system forward, and this rear inflow jet would get really intense and mixed to the surface here at the front of the system and cause very severe wind gusts. And this is typical sounding for such a case. And now we want to have a look at the model data, and they show a potential outbreak of very severe storms too. This is our IGT2 model. It's our regional model with a resolution of 2 kilometers. It's the simulated reflectivity. And at 16 UTC, you see here such some storms, which are clusters here to a line. And then it develops into such a bow echo. Here you can see clearly this bow echo, even the rear inflow jet, which evaporates the precipitation at this region, was forecasted and pushes the system forward to the Rhine-Main area. It's here near Offenbach, near Frankfurt. There's a very dense population, and this would be really severe. Especially remember there are a lot of public viewing events there, and even at the red show was possible. And this was the forecast from the wind gusts. They go up to 150 kilometers per hour and spreading out in the Rhine-Main area. The red color is above 100 kilometers per hour. This would be very severe. Generally, we knew that IGT2 overestimates convective wind gusts, but when you see such high gusts with such well-predicted system, you get really, really nervous because the other high-resolution convection allowing models that predict this similar. And also in the IGT2 ensemble prediction, there was a high probability of gusts over 25 meters per second in this area. It's around 70%. And remember, you have a resolution of 1 kilometer, and these are very high probabilities. So we made a pre-warning for this area early and advanced, so that many public viewing events were cancelled as a result. But it wasn't an easy situation, as we see later. What will happen here? You see at 14 UTC here. The cluster should develop here out of this region when you remember the model forecast, but there were a lot of cirrus clouds here from this cluster over Switzerland, and this might be depressed insolation, but there are already thunderstorms at the cold front here and some bigger storms here. And then let's see what happened. You see here, there was a MCS, mesoscale convective system, with lots of overshooting tops, strong divergence at upper level, big angles, fast-growing angles, and there's always a hint to severe weather and densifying storms. So you have seen this satellite pictures, and you have seen the model forecast, and now I ask you to make a forecast how will the maximum measured wind speed in Germany will be. You think it's below 80 kilometers per second or even bigger than 140 kilometers higher than 140 kilometers per hour. 80 to 90. One says there will not having much at all. One goes to up to 120 to 140, 105 to 120. Okay, good. Okay, we will see what happened. Here, you see this radar reflectivity here and the model simulation here in this. And at first, at 15 UTC, it was quite good forecast, but here there was a lot of precipitation out of this angle. And so these storms here in the forecast were not able to initiate. And here you see already a big cluster, which is very small here. And I think this is due to this precipitation and the lack of insulation here in this region. There were not developing so strong storms. These were already supercells, but they were so intense they couldn't use this full potential. But when you see here, instead of this region, the cold front, at the cold front, there was a very well developing squall line. It even could be a bow echo pushing to the northeast here. And from this cluster, which should hit the Rhine-Main area, was only this thing here left. It was a small line with really intense wind gusts, but it wasn't that intense bow echo, even the retro, which was forecasted. And let's go more into the evening hours. You see here that the storms clustered together, and this was only the southern storm here, or the southern part of the line, which produces the strongest wind gusts. And so the Rhine-Main area wasn't hit so much by the storms. And when you have a look at the temperature radar reflectivity with the temperature, you see that the squall line is running into a stable air mass. There was already colder temperatures ahead of this with 20 degrees, only 20 degrees were 28, 29 degrees. And so it was not so effective here because the storm got elevated. So there were problems to mix the wind down. Only here in this area, this part of the line was really severe, and there were a lot of wind reports. Most of them were by fallen trees in this area here. Most from this is the southern cell, but these are the measured wind gusts, and in general, the measured wind gusts barely reaches 100 kilometers per hour. There was one measurement with 107 kilometers per hour, but it wasn't that event what was expected. And let's come back to the European Football Championship. The DWD was responsible for the weather forecast for this championship, and released our forecast before the game. This was the forecast. There was a high probability of thunderstorms here, so we put the thunderstorm sign here. And the game Germany versus Denmark was in Dortmund. It's located here. And I don't know if you have seen it in TV. They were hit by a thunderstorm. And you see that there was heavy precipitation, light flashes. Fortunately, it was an elevated storm, so there were no severe wind gusts, but very strong rain, so the game had to be interrupted for 20 minutes. And fortunately, there were no casualties, because this is very dangerous, such situation. You have a lot of people there, and there's such strong lightning here. Let's have a closer look at the cell. You can see this at the sandwich RGB here. And it's already a stronger cell. You can see some overshooting here. Maybe will be some penetration of the of the tropopause. It's a little bit intenser storm, but the line will be here. This will be more intense, and in the radar picture you see the storm. And the radar drill down here wasn't the highest reflectivity, around 60 dBz. Were not so high in altitude, but it was enough for small hail in this region. Here's the stadium, and our mesocycline detection algorithm even detected rotating updraft here. You can see here such a kind of inflow, and was a little bit rotating this updraft for 1 or 2 time steps. Then the storm was weakening again. So at the next time, this violent air mass was pushed to the east. The cold front went through, and there was a little bit stabilization, and this air mass affected the eastern parts of Europe. And at that day, I take a plane to the EUMeTrain ESSL. EUMeTrain ESSL testbed, and when you have the chance, I highly recommend to take part at such a testbed. I learned really a lot there, and it was on the plane to Vienna, and I saw the towering cumulus clouds here, and I think it must be one of these towers here. It was really impressive. Here was a bigger system I could see from far away. So let's go to the conclusions. Yeah, we had NWP models and ingredients which showed a severe storm outbreak. There was a special situation due to the public viewing event, despite some reports of damage. Fortunately, there was no extensive damage, and the question is why? Why was there no such severe thunderstorm? And I actually didn't really know. Maybe despite increasing automatization and the use of artificial intelligence, nowcasting will retain its importance in such cases in the future. And so far, that's my conclusion for this case. And at last, are there any questions so far? Okay, so let's go to the last 10 minutes. Have a look at the actual situation. I will start with the Airmass RGB and the 500 hectopascal geopotential. And you see this strong long wave trough over Western Europe, and Central Europe is ahead of this trough. And there's a stronger blocking high pressure system over eastern parts of Europe, and the circulation pattern remained all the summer, and this southwesterly flow will go on. And you here the IPV values, you can see this trough, well pronounced trough here. Let's go to the sandwich RGB, and you see that in the morning hours there were already some thunderstorms here and over Germany. Also Offenbach was hit by a weak thunderstorm, and one very good developed storm was in the morning hours here over northern Italy. You can even see here a flanking line. I think this is a flanking line where you have the inflow of the storm and the overshooting tops, and you see here in the anvil gravity waves. Usually you have this gravity waves in stronger storms, and you can see this because the sun isn't so high, so the angle with the sun is very low, and sometimes you can see this in the morning hours or in the late evening hours. It was really a nice storm, and I think there will be severe hail at that. But have a look at the current situation. It was at 6 UTC today. I put it bronze in it, and the isolines with the mean sea level pressure here. This another blocking high pressure system over the Atlantic, and here is this well pronounced trough, and here is this blocking high over Eastern Europe. Here are some storms in the warm sector. There was a very warm air mass here affected in southeastern Europe. and maybe this year, maybe a convergent line here in this warm air, and often that's called the heat dome. You have 850 hectopascal temperature above 20, even here 25 degrees, and this will lead to very high temperatures. I think 40 degrees in some region here we will see in the next days, and I think you can call it a small heat dome. And in the flanks of this heat dome, you have often severe thunderstorms, and this will be the topic for the next days. There's a lot of cape here in this area at this flank. There's this warm front and this cold front, so we will see thunderstorms over Germany too, but there's good shear in our region, but more of interest will be this region here. And so there was a sounding available once here from Czech Republic. It's model sounding from IDT2 model, and this shows a lot of cape here, and it's very moist profile. You have not so much sun, so I think the storms will be cluster very fast. The shear with 17 meters per second is sufficient for supercells, so we will see a mixture of multicells, clustering multicells, and also perhaps some supercells producing strong hail. But I think the main threat will be excessive precipitation, because you have here also this deep warm layer here with deep warm rain, and I think it will give you a lot of precipitation, flash flooding. This is a sounding from northern Italy. And this looks a little bit different because you have this very dry boundary layer and a very dry layer in the lower troposphere, and this looks like a little bit an inverted V structure. That means when the precipitation is falling in here, there will be evaporation, there will be eventually severe downbursts here when we have a supercell, but I think we will get some problems with the convective initiation because you have a lot of thin here, convective inhibition with minus 50 joule per kilogram. So I think the thunderstorms will go more into the Alps, but there we will see, I think, a few hail reports, and also severe wind gusts. Shear is quite good with around 20 meters per second. Then see what will happen in the next days. You've already this trough, and there will be a cyclogenesis here at the northeastern flank. This warm air is pushed a little bit to the east, but this heat dome here remains, and I think the thunderstorms will concentrate on this area, and there's quite a good overlap, especially in the direction of the low pressure system here between Cape and shear vector, so that there will be some lines or supercells or bone segments. So it's a rather complex situation here, but I think in the next day we see in this area here a lot of reports of severe weather. And in general, in the circulation, it will change not so much. This trough is going to the east, will be blocked by this high pressure system here, and another trough is approaching from the Atlantics and regenerates this trough. So there will remain a southwesterly flow over central parts of Europe, and very warm conditions over Eastern Europe. You can see here, and will be already the chance of thunderstorms for Central Europe at the beginning of the next week, and at last we will have some extended outlook from the IFS model, and for the next week we see this high temperature anomaly over eastern parts, where in the western parts of Europe you will have this colder temperature around, even below the mean values. And then let's look at a week forward at the end of June. Maybe that the trough is moving more in the Central Europe, so that you get your lower temperatures. There are still signals for temperature above average over the Eastern Europe. But I looked at the cluster analysis at the morning. There might be some clusters which show a change. That here, that we have here reaching over Western Europe and a trough here over the northeastern Central Europe, and so it might be that the thunderstorm will shift to the east, and in the Western Europe we get more stable conditions, but it was only one cluster of three cluster. So I talked a lot. Thanks for your attention.